Friends, welcome to the 16th lecture under the NPTEL course on offshore structures and the special loads. In this lecture, we are going to talk about some uncertainties involved in the analysis and design very briefly. There are different types of uncertainties which actually introduce complexities in analysis and design. These uncertainties can be grouped. Let us say the first level or the first group. These are uncertainties which are related to material characteristics, like yield strength, Young's modulus, Poisson's ratio, etc. The second group of uncertainties are related to uncertainties in loads. One is material, other is loads. This can be further subdivided in two groups. Let us say under static conditions, where we say for example dead load. It may not have any major uncertainty, so it can be omitted. Live load, it may have large extent of uncertainty depending upon the designer's choice and so on. The second subcategory under the second group could be under dynamic loads. Under dynamic loads such as earthquake load, wave load, wind loads, etc., which are random in nature, uncertainties are very high. Or I should say very significant. Now, uncertainties associated with dynamic loads are generally larger in significance compared to those that of static loads. That is the first observation. They are also larger compared to those associated with material. Interestingly, dynamic loads also affect material characteristics. That is a very interesting statement. Let us say for example, we will talk about dynamic modulus of elasticity, E dynamic. E dynamic is ratio of stress to strain under vibrations or vibratory conditions. How they are computed? This is computed either from free forced vibration tests in shear, compression or elongation. Generally, this property is more prominent for viscoelastic material in purely elastic materials. Stress and strain occurs in phase, so that the response to stress, that is strain, occurs simultaneously with each other. But that is true only the material is purely elastic, but in viscoelastic material stress and strain will actually have a phase lag. Strain usually lags stress by pi by 2 radians. So, strain lags stress by pi by 2. So, phi, which is the phase lag, is actually pi by 2. So, strain is E 0 sin omega t, whereas stress is sin 0 sin omega t plus phi, and we know omega is 2 pi f, where f is the frequency of oscillation and phi is called as phase lag. Generally, modulus of elasticity is described, or let us say defined, as stress strain behavior under monotonic loading. Whereas, dynamic modulus of elasticity describes behavior under cyclic or vibratory loading. So, friends, in a case where the load process is highly dynamic in nature and random, which has got lot of uncertainties, we should have a thorough idea about the dynamic modulus of elasticity of the material which should be used in the design. Let us ask a question: what are the factors that affect dynamic modulus of elasticity? 1, it actually depends on the material on which the experiment or experimental investigations are carried out. As very clearly stated by John S. Popovich, Jerzy Jamatis and Iosif Shiklonik 2008 study on static and dynamic modulus of elasticity of concrete, which is an ACI CRC report. The second factor is that the dynamic modulus of elasticity values of concrete obtained by different tests do not agree. There is a wide variation. The dynamic modulus of elasticity values obtained from pulse wave propagation measurements are higher in comparison to those obtained from vibration response measurements. In fact, dynamic modulus value also depends upon the type of experiment you conduct. When even carried out on the same specimen, the test methods give you different results. The fourth factor, dynamic modulus of elasticity computed from a prismatic section is different from cylinders of the same concrete mix. So, E dyne is function of 1 shape, 2 size, 3 type of experiment, and 4 a strong disagreement between different tests. There is a wide variation. Let us see one by one by different tests how ED can be calculated. Let us say E dyne based on longitudinal vibration frequency. Please understand, dynamic modulus depends on very strongly the type of experiment you perform. This is as per ASTM C215. It has got some basic assumptions. The test is performed on one dimensional specimen. The test shows plane section motion only, no bending. So, E dynamic is given by V p square rho 1 plus mu 1 minus 2 mu by 1 minus mu. I call this equation number 2, where V p is called the p wave velocity, mu is called Poisson's ratio, and rho is the mass density. There is another method by which you can compute dynamic modulus of elasticity. This is two frequency method, which is proposed by Lau 1994 and Subramaniam et al. 2000. So, Lau AEH 1994, mathematical theory of elasticity, Dover publication, Newark. Subramaniam KV, Popovics JS and SP Shah 2000, determining elastic properties of concrete using vibration, resonance frequencies of standard test cylinders. Cement, concrete and aggregates, ASTM 22.2.81.89. So, according to two frequency method, dynamic Poisson's ratio is estimated, which is given by A1 F2 by F1 square plus B1 F2 by F1 plus C1, where mu d is called dynamic Poisson's ratio. F1 is the first longitudinal frequency in hertz, F2 is the second resonance frequency in hertz, A, B1 and C1 are actually constants which depends upon the dimensions of the cylinder. Once I know the dynamic Poisson's ratio, I can find dynamic modulus of elasticity as twice 1 plus mu dynamic rho 2 pi f 1 r 0 by f n dash square, where r 0 is the radius of the cylinder and f n dash is given by a 2 mu dynamic square plus b 2 mu dynamic plus c 2, where a 2, b 2, c 2 are constants and they depend on dimensions of the cylinder. As given by Subramaniam et al. In 2000. Now, interestingly, let us have a relationship between the conventional Young's modulus and the dynamic Young's modulus, which is connected by this relationship or 1.25 E dynamic minus 19 is E, as given by Neville 1997. So, Neville AM 1997, properties of concrete, 4th edition, John Wiley, New York. Having said this, let us now understand uncertainty in third group. Third group essentially arise from the mathematical modeling and methods of analysis. So, interestingly, let us talk about the nonlinearity or nonlinear term in drag force in Morrison equation. Morrison equation is used to determine the hydrodynamic force on offshore members. Force on a cylinder is given by Morrison equation, which is based on experimental studies. They actually postulated an empirical relationship to estimate forces on cylinders given by Morrison, J.R. O'Brien, M.P. Johnson, J.W. and Schaff, S.A. in 1950. Force exerted by surface waves on pipes, petroleum transactions, AIME 189. So, according to them, f of zt is C I v dot x plus C D v x v x, which is inertia term plus drag term. This force will be acting in the direction of propagation of wave, that is in the forward direction. Water particle velocity and acceleration are evaluated, maybe for example using Airy's theory at the centroidal axis of the cylinder. C I consists of two terms. One is the hydrodynamic mass contribution, and the other term is arising due to variation in pressure gradient. Between, or let us say within the accelerating fluid. So, C I has got two terms, C A, which is C m rho pi d square by 4 plus rho A, which can be said as C I rho pi d square by 4, where C I is the inertia coefficient for the section, C m is the added mass coefficient, A is the cross sectional area. Therefore, inertia force per unit length of the member is given by F I at any specific location Z t is C I V x dot, which is approximately C m V x dot plus C A V x dot, which can be Cm pi d square by 4 rho Vx dot plus rho A Vx dot. Let us call this as equation number 2. We also know that the drag coefficient is function of Reynolds number. So, C d half rho C d dia is actually also a function of Reynolds number. When you apply this in Morrison equation, it gets squared off. So, let us talk about linearization of the Morrison equation itself, because Morrison equation has a term C d Vx Vx. So, this need to be linearized. So, let us say f is Cm Vx dot plus C d bar Vx plus C a Vx dot plus C d Vx minus C d Vx, which can be Cm Vx dot plus C d bar Vx plus C a Vx dot plus E, where E refers to error in the equation, which is nothing but a specific error function. So, essentially the objective is to reduce this function to 0 by minimizing E. So, let it be minimized by least square technique. E square by dou C d should be minus 2 of less than, let us say, C d Vx minus C d Vx square. So, the symbol indicates time average. C d bar is C d Vx square Vx by Vx square. Hence, for a Gaussian process, with 0 mean, Vx square is sigma Vx square and Vx time average will be root 8 by pi sigma Vx, and time average of Vx square Vx can be root 8 by pi sigma Vx cube. Hence, C d bar is C d root 8 by pi sigma Vx cube by sigma Vx square, which can be CD root 8 by pi sigma Vx. So, it is important and necessary that distribution of Vx is to be determined, because we need sigma Vx. Then only CD bar can be computed. For surface elevation, eta be a Gaussian distribution, V, that is water particle velocity, will also follow Gaussian distribution. Hence, linearized Morrison equation is given by f z of t c I v x dot plus c d root 8 by pi sigma v x v x, equation 4. So, that is the linearized term what we have, which is again an approximation of one important drag nonlinearity coming down from the equation. So, friends, in this lecture we discussed about two levels of different uncertainties, one from the load side, which is the drag nonlinear term in the Morrison equation. The second one is the dynamic modulus of elasticity, which is actually the relationship between stress and strain under vibratory conditions. So, we have seen how we can estimate them more appropriately by the given empirical relationships of different researchers in this lecture. Thank you very much.